All right, can you guys see my screen? Yeah, I think so. All right, so the birthday paradox is a fun way to think about probability because it forces us to reorient the way we understand the way that computing probabilities works. It's not actually a paradox because it's not contradictory in any way. It's just that for a variety of biases that we have, it's not necessarily immediately intuitive to us that the math really works out. So the basic crux of the birthday paradox is, what are the odds that somebody in a room shares a birthday with one another? And you might be thinking to yourself, that probability sounds pretty easy, right? My birthday is 1 in 365, so the odds of a match have got to be that. It doesn't quite work that way. So one of the reasons the so-called birthday paradox seems like a paradox is that we're starting with an assumption that we can all sort of similarly understand and take to be true. If we're thinking about what are the odds that somebody shares my birthday, we're thinking to ourselves, the odds aren't great. I have a 1 in 365 birthday, and the odds that someone else has that 1 in 365, there's just so many other options. If you want to find someone that shares your birthday, you'd probably just Google celebrities that share your birthday. I don't know about you guys, but I share a birthday with Clint Eastwood and Colin Farrell, and I'm okay with that. Do you have any cool celebrity birthday twins? I'd love to hear about it. But likely you're thinking to yourself, if you just pop me into a room with a bunch of randoms, no one's going to share my birthday. That seems pretty extraordinary. If you reorient the question to ask yourself, what are the odds that in a room full of people, there's some birthday pair in there? The answer is that statistically, the odds are surprisingly high. You might be thinking to yourself that the odds as they pertain to you just sort of carry over to every other individual in the room. Again, the numbers aren't exactly going to work that way. I'm going to show you why. Interestingly, if you're charting out the probability distribution as it pertains to the birthday paradox, it only takes a room of 23 people for there to be a 50-50 chance that there's a birthday twin somewhere in the room. Once you get up to a room of about just under 50 people, you're talking almost 100% certainty that there's going to be a birthday twin in there. And again, you might be thinking to yourself, how does that work? How does that make sense? Wouldn't you need 365 people in the room? Not quite. So you want to reorient the way that you're thinking about how probabilities work. So you can start from an assumption that, again, we can all take to be true, the probability that two people have different birthdays. We know that that's going to be quite high. Okay, and if you were to chart the probabilities of two people having different birthdays, one way to do the math would be to look at it like this. You could plot the probability that somebody, namely you, has your own birthday, which is 100% chance that you have your own birthday. Let's say we're talking about me. My birthday is May 31st, so the probability that I share a birthday with myself is 100%. You would multiply that probability against the probability of the next person. The probability that the next person is going to have a birthday that's not May 31st, that is quite high. 365 and 366. Well, the reason I'm using 366 in here is to account for the potential for leap years. You can use 365 in this and it doesn't really change the probability all that much. But if you want to take the chance that somebody in the room has a leap year birthday, you can use 366 if you want. So the probability that somebody has my birthday of May 31st, if I was just to approach any person and get their birthday, the odds that we don't have a match, again, pretty near 100%, 99.73%. So there's less than a 1% chance that if I approach a single person, we have the same birthday. If we're talking a room full of people, you're going to have to do this process iteratively, meaning you're going to have to do that math over and over and over to account for multiple comparisons. So now let's say we have 3 people in the room. What's the probability that 3 people have different birthdays? You continue that iteration. So what we have here is, again, that same probability that I have my own birthday. The next person is not going to have their birthday of May 31st. And the third person, their odds of not having a birthday of May 31st. But think about what's different now that there's 3 people in the room. It's not just them being compared to me, they're also being compared to each other. So what we have, the more people we add into the room, are more opportunities to find a match. When you have more people in the room, it's not just about asking, do people share my birthday? It's do they share my birthday or do they share a birthday with each other? So if you were to do that iterative math, things change a little bit. Again, in a room of just 3 people, the odds that all of us have different birthdays is again quite high because you're just dealing with 3 people. The probability that 3 people plopped together in a room have a birthday match is still quite low, but a little bit higher than just comparing 2 people. Let's say we had an average classroom of 293 students, let's say a room of 40 people. This demonstration always crushes it in a full classroom in person because there's twice as many people as in the summer section, but we're just gonna play the math, we're just gonna play the game anyways. But let's say we are in a standard 293 classroom of about 40 people. Think about how many times you're having to do that iterative probability. You're comparing me to those 39 other people. So that right there is a whole lot of potentials for a match. But then you're comparing that second person's birthday to all of the rest of the 38 people. And again, those are all probabilities. Those are all possible opportunities for a match. So think about when you're comparing everyone to everyone else, how that probability rises exponentially. So what if you crunch the numbers on the probability of a match in a room of 40 people? Damn near 90%. Okay, the odds once you get up to a room of 40 people is very, very high that there's going to be 2 people sharing a birthday. And in my experience, having done this demonstration twice in a room of 40 people, we always found a match. So this is the birthday paradox. Like I said, it's not actually a paradox. It's just us not intuitively getting the nature of exponential probabilities. It's not a paradox. It's just that we have a hard time comprehending it for a couple reasons. One is that our brains don't quite wrap our head around exponential probabilities, right? Again, we're just thinking of that comparison between our birthday and someone else's birthday, our birthday and the second person, and we're not able to really fully grasp just how fast exponential probabilities rise. And the fact that just adding one other person into the room doesn't give you a 1 in 365 shot. It's going to be a series of comparisons that exponentially rise the likelihood of getting a match. Additionally, this is an interesting spot in learning about statistics where our biases can sort of keep us from fully understanding what's right in front of our face. We're kind of self-centered in the way that we naturally think about ourselves. And so what's the likelihood that somebody shares my birthday? And we sort of let that thinking spill over into our understanding of this probability problem. It's not just about finding a birthday pairing with you, although it's always fun to find someone who shares your birthday. It's what are the likelihood that there's a match somewhere here in this room. And so we have to sort of get rid of that sort of self-centered thinking to fully wrap our head around what this probability is. So, like I said, in normal semesters of 40 people in the room, we try this, it's gangbusters. We're still gonna try it even though there's like 4 of you in this room. We have everyone else's birthday from the class. I've got that here. I made Chris enter the game, so he's gonna be compared to all you. Maybe one of you guys has a birthday twin in my partner, Chris. We're gonna see. So we're gonna try it out. So here's how this should go. First, we're gonna go to the birthday paradox probability simulator. That was at that link that I showed you a few slides ago. I'm gonna open that up and show it to you. What are our odds of a match based on how many people are going to be compared? And I'm gonna list everyone's birthday. Normally what we do is everyone goes around the room and says their birthday out loud. I have a list of everyone's birthday here, so I'm just gonna draw it out for you. If at any point you see a match, call it out and we'll have our birthday twin. All right, so now let's pop on over to this birthday paradox link that I showed you. This article here is a really great read on the birthday paradox. It really gets into the math and it can help you understand what exactly the birthday paradox is all about. And there's also a video tutorial in here that's also linked in the slideshow for if you want to get a refresher on how the birthday paradox probability math works. It's about a 7-minute long video. It's a pretty quick view. So here in this article, we have a simulator to figure out the probability of getting a birthday match with a certain number of people. So with everyone in the class, with me, and with Chris, who generously agreed to be part of our demonstration, 27 people are going to be compared. Okay, so we're going to leave it at 365. We could make it 366 if we wanted to take into account leap years, but I want to boost our odds. 27 people, run the math. This here is our chance of there being a match. So the chance of getting a birthday twin between 27 people is 61.82%. Do you guys want to take those odds? Somebody give me a sign. Sounds pretty good to me, right? 60% likelihood of getting a match. Would you bet money on that? Let's try it out. All right, I got my list of birthdays. I've got my whiteboard. I have not figured out a way to get past the fact that this is a mirror image. Are all 4 of you capable of reading backwards? I can't write backwards. I feel like that's way harder. Is it a mirror image? I don't know. We're just gonna have to go for it. All right, I've got the birthdays, I've got my whiteboard. Oh, really? So I just see it backwards? Oh, magic, how does that work? All right. Let's party. All right. First things first. First birthday on the list. We've got Chris with July 26th. So far, so good. Can you see that? It's a little bright. All right. Next up, yours truly. Yes, I turned 32 on Sunday. And yes, I made myself a funfetti cake. Okay, maybe I have a birthday twin. The first time I ever did this demo, I was the one with the birthday twin. So feeling very blessed. Next up, Catherine, your birthday is April 15th. Tax day. Right? All right, let's see. Haley, we've got December 16th. All right. Sammy, we've got March 3rd. All right, next up, number 6. Carolina has October 19th. And if you think you see a match at any point, Yahtzee. 7, Danny with July 21st. Oh, is this with Krish? Let's see, Sam F with a December 15th. We got cousins, not twins. That might be the best we can do. We'll see. All right, next up, number 9 was Ryan with a December 18th. You like how the farther I go over, the worse my handwriting gets? Can you still see? Okay, let's see. Number 10, Tinchi with November 2nd. Madison G, December 12th. All these December birthdays played me so hard. Bryn, number 12 is Bryn with October 21st. Molly with February 11th. Jerome with May 17th. Gabby with December 26th. I always ask people who have their birthday right around the holidays, like, do you like that? And do you get twice as many presents? If you don't, I will fight on your behalf. You deserve twice as many presents. That is so bullshit. Seriously, do at least your parents get you two? That's just not right. It better be a car if it's going to be a combined birthday present with a Christmas present. I swear, that's just not right. All right, 16, Nicole P with September 12th. 17, Zoe with March 26th. Madison P, August 7th. You almost had a birthday match with my best friend from home, but you were a couple days off. I was about to call my mom and be like, Mom, be in my birthday paradox demonstration. But didn't get a chance. All right, Morgan. We've got May 14th. Number 20, Jenna with February 8th. Caitlin, April 21st. 22, Hilia with March 7th. 23, Tolly with June 2nd. Happy birthday! I hope you get lots of presents today. And Lauren, June 1st. Oh, we were so close. Again, I hope you got lots of presents. If you're anything like me, you had a few champagne cocktails, ate some cake, ate some pasta, and that was all you needed. Quarantine birthdays, as long as you eat everything in sight, are not that bad. All right, 25, Sam W, September 15th. That was kind of close. All right, we're down to the wire. Selena, March 12th. Was that anywhere? Oh, bother. Last up, now Jing, September 30th. That's just the way the cookie crumbles. I don't see a match here. Do you guys see one? I see a couple birthday cousins. Looks like that's as good as we're gonna get. So that's just sort of the way it goes, right? How much was the probability? It was 61.82%. So nothing approaching a sure shot, but you know, I liked my odds and I was optimistic. Like I said, whenever I've done this in a room of about 40 people, we've found a birthday match both times. So unfortunately, I am left disappointed here today. We do have some birthday cousins and we do have some birthdays from today and yesterday. So Lauren and Talia, I hope you guys are having an excellent birthday. But there's the birthday paradox demonstration. It's just basically a demonstration indicating that probabilities can surprise us even when the math is pretty straightforward, and that, you know, the odds of having a birthday twin when you're in a large group of people is surprisingly high. So the next time you're in a room of 45 people, say to yourself, we have almost 100% shot of having a match. Let's play the birthday paradox game and see what happens. Because it's always more fun when you have a birthday twin. And